Thank you for that introduction. Like Lauren said, my name is Alison Farrish, and I'm going to be talking to you about the physics of exoplanet host stars. So stars in other solar systems that have their own planets orbiting them. So exoplanet discovery is a really interesting and cutting-edge field, and it's actually a fairly young field. So as recently as the late 80s, early 90s, we didn't know there would be planets in other solar systems. We only knew about the planets in our own solar system. So it's pretty incredible that in the last 25 years alone, we've found and confirmed over 4,000 exoplanets. A lot of them are gas giants like Jupiter and Saturn, some are more Neptune-like, but what we're really interested in are these guys, the terrestrial planets. And that means Earth-sized planets that are thought to have rocky bodies. And you can see we've only found about 160 of those so far, so exoplanet detection is still a growing field, and that number will grow in the future. But we really want to think critically about what these terrestrial planets might look like, how they might be similar to Earth or different. And one way that astronomers have developed to think about that is this concept of the habitable zone. So it's sort of a Goldilocks zone, not too hot and not too cold, just right, where the planet is able to support liquid water on its surface. And that's extremely dependent on the temperature of its host star. So our sun is a nice 6,000 degree Kelvin star. We are sitting in its habitable zone here. For larger, hotter stars, that habitable zone is farther out. And for the smallest, coolest stars, what we call red dwarfs or M dwarfs, that zone comes extremely close into the planet. So that's an important consideration when we're thinking about planets around other stars. So there's been a lot of really interesting discoveries, and there's been a lot of buzz about certain exoplanets. For example, the TRAPPIST-1 system, which is a stellar system that has 7 Earth-sized planets. You can see that the illumination from the host star, that's that sort of Goldilocks temperature, is comparable to Earth, Venus, or Mars. This planetary density is also comparable, so we do think these are terrestrial planets. And they're similar in size, physical size, to Venus or Earth. So you might think that's a wonderful system that we're going to go build trains and cities on those planets someday. But I'm here to rain on that parade just a little bit. So as I said, when we think about these Earth-sized planets that are being found around these small, cool stars, it's an attractive idea to think of them as having just that Goldilocks temperature and being beautiful, temperate worlds. But again, when you have the habitable zone around an M star, that's extremely close into the star. And at that extreme proximity, we have to think about other effects from the magnetic activity of the host star. So you might have a planet that's being strongly bombarded by flares, coronal mass ejections, energetic emission, particles being accelerated by strong magnetic fields, even direct magnetic connection between the star and the planet. So you might get rains of million-degree plasma falling down onto your planet. So these are pretty important considerations when you're talking about a habitable world. And when I say we're talking about close-in planets, I want to drive home just how close in. So these are to scale. This is the orbit of Mercury around our sun. Mercury is our innermost planet with a year of 88 Earth days. And that's actually pretty far out compared to some of these Earth-sized planets we're finding around M stars. So Ross 128b is an Earth-sized planet around an M star, Ross 128. And it's actually whipping around its star every 10 Earth days. So it's extremely close in. And it's not the full picture to say that this is in a nice Goldilocks temperature, because this extreme proximity is an important consideration. One way we quantify that is with this quantity called the stellar Alfvén surface, and this is roughly to scale as well. So the solar Alfvén surface is well inside the orbit of Mercury. Earth and Venus are not affected by this critical boundary, but the planets around these small M stars are in this regime where we have to consider the dynamics of the star itself. So what exactly is that boundary? It's a critical surface inside of which you're magnetically connected back to the star. So if you're inside that Alfvén surface, you're directly inside the atmosphere or the corona of your star. And so some interesting work that we've been doing at Rice is modeling where that surface might be. So these curves represent where the stellar Alfvén surface is for various stellar activity levels. And this is your distance from the star. And we're finding that a lot of these planets that people are saying are exciting habitable worlds are actually residing inside the star's atmosphere. So that's where you could get strong interaction with the star, those rains of plasma, and all this kind of dynamic activity that we really need to factor into our habitability picture. So these are the TRAPPIST-1 planets. That's Ross 128, as I said. Proxima Centauri b is our nearest neighbor. And these are all kind of unfavorable for habitability from what we've been studying. This is a little teaser that this planet is maybe in a more favorable orbit, but a lot more modeling and observations would have to go into that. So I want to leave you with just a few conclusions. The search for habitable life is a really exciting field, but there's a lot more work to be done. Particularly, we need to consider exoplanet host star magnetic properties. They're vital to understanding the planetary environment and the potential for habitability. So we're not packing our bags just yet to move to any of these planets. That's a little ways off, but thank you very much.